have been discussing ferromagnetism starting from Heisenberg model. So, our purpose is to try to solve Heisenberg model if that is possible, and I argued that it is not difficult to solve the Hubbard model in the ferromagnetic limit, while it is extremely difficult to solve Hubbard model in the anti-ferromagnetic limit. And indeed, anti-ferromagnetic Hubbard model anti-ferromagnetic Heisenberg model has been solved only in one dimension by a very famous calculation, which is done by Hans Bethe in 1931, and that method is an iconic method in the mathematical physics of this kind of models, and that is called Bethe ansatz. He used an ansatz to solve this problem. It is a tour de force mathematical calculation, and it is a hallmark of a genius doing mathematical physics, and is of course one of the great physicists of the last century. The point is that the Heisenberg model in the ferromagnetic limit, which means all Jij's are positive, is not so difficult to solve, and then we try to solve it using our intuitive understanding of what should happen in this kind of a model. Remember, classically you can easily guess what is going to be the solution. It is interesting that for ferromagnetic Heisenberg model, your classical guess works out, and that is the quantum ground state as well, as we will show below. Now, how do we choose this ground state? Okay. So, we have to choose a quantum mechanical state and a wave function for the entire spin system, which is basically thermodynamic in number. So, you choose this ground state based on your classical assumption that you see, if all the Jij's are positive, then this Hamiltonian should give me all spins up. That should be the lowest energy state, and magnetic field of course chooses what is the up direction. So, that is the that is the direction we call up, z direction. Okay. Now, how do I write such a ground state? Well, that is not difficult. What we do is that you just come to every site, take the projection of the spin along that z direction and make it maximum as large as possible. And what is that maximum value? That value has to be s, the value of the spin. That is the maximum projection that you can have. So, so s is actually s is given by the maximum projection, and so that is the maximum moment that you have at each site in the direction of the field, and so you just take that and take a direct product of all these states in the to form the ground state. Okay. And to be more precise, because we are doing quantum mechanics, I also define the operation by the operator Sz of the ith site at the state at is at the Sz I equal to s at the ith site, and that state, that operation will give me just the maximum value of s, which is s. So, Sz operating on s will give me s if the projection is maximum, which is s, and that is what is written here. Okay. So, that is the starting point. Now, we want to rewrite the Hamiltonian. How do I rewrite the Hamiltonian? Well, the standard method is to use these operators, raising and lowering operators, which you are familiar with in quantum mechanics, which are Sx plus minus I Sy at every site. So, for ith spin I will just put an index I here. Okay. So, how does it help? Well, I will just show you how does it help, but before that let me just write down the as I wrote down earlier, the commutation relations are like this: Si alpha Sj beta equal to I h cross epsilon alpha beta gamma S gamma Si gamma. Okay. Now, if I and j are different, then of course, I have to put a delta I j here. So, if I, so that is equal to 0 if I not equal to j. Okay. So, that is the caveat that one has to remember, and that is something I will be using in this derivation of Heisenberg ferromagnet. Okay. So, let us write down this term S dot Si dot Sj as S x I x S I S j x plus S I y S j y plus S z I S j z. So, that is just the dot product of these two, but then what I will do is that I will keep this of course intact, but I will write this as a combination of S I plus S j minus plus the Hermitian conjugate of that. This I leave you to go through. Remember that there will be a half. So, this will be, this you can show easily, basically write S as this, and this is just the Hermitian conjugate of this operator, and then you what all you do is just take the product, just do the algebra, and what you will find is that this reproduces these two terms. Okay. So, and because it is the other thing that you have to remember, that since I and j are different sides, you can always commute these spins. For example, Si x Si y is not equal to Si y Si x, but Si x S j y is equal to S j y Si x because they commute. So, that is something you can use, and that means S plus at site I, S minus at site j, these will sorry, I am using up and down at the top. The notation I am using is plus here, minus here. Similarly, here also I will do the same thing. I will write plus minus here, plus minus, okay, S plus minus. Okay, so this is this can be written as S minus j S plus I, because the I and j are different sides. So, these things commute. So, if you do that, then what you will end up with is a Hamiltonian of this kind. So, you can just commute, and then what you will have is, the idea is that why do you want to write it in this way? The main purpose is to write this term as some S minus I S plus j. That is what we are trying to do, this term. You will immediately see when I go to the next step why one wants to write this, and this is the term that is you can write using these commutation relations, and you can just switch the terms in such a way that the plus j appears on the right. Okay. Now, let us go to the next step. When Sz suppose at a site I Sz is equal to S, well, at site A, then in that case if I apply S I on that S I Z equal to S, then I will get 0, because this is the maximum value of S already attained by this Z component. If I want to raise it further, I will not be able to do it. So, I will get a 0. So, that is the reason I have taken S plus on the right hand side. So, now if you look at this Hamiltonian, if this Hamiltonian acts on the ground state, then I need to do two things. One, I have to first show that it is an eigenstate, this one is an eigenstate. So, to do that I have to show that H 0 equal to some E times 0. So, this is something I have to show, that is number 1. Number 2, find E 0. Okay. And then of course, to show that this is the ground state, then I have to show that E 0 is the lowest energy state. So, that is all we are doing. This is the ground state. We are trying to figure out what is the ground state. So, there are 3 steps. One is that I will use the Heisenberg Hamiltonian to operate on this chosen state 0, and first I have to show that the chosen state is indeed an eigenstate. Second, I will have to find out the eigenvalue, and third is that I have to show that there are no other states which gives a lower eigenvalue. So, the E 0 is the lowest energy state, E 0 is the lowest energy, and that is 0 is the ground state. No other state has lower energy. So, these are the 3 steps I am going to take. Now, because of this property, if I apply the Hamiltonian on that state 0, H operating on 0, H has these 2 terms, half J I J S I Z S J Z minus half S minus I S minus plus J, this operator, and minus H times S I Z S Z I, then I will just operate this on this. Now, let us see what these terms give. See, these are both S Z operators. So, that will simply give S square from here, right. So, minus half S square sum over J I J. So, that is the first term, and that will of course give me back 0. So, that part gives me the is like an eigenvalue equation. Let us look at the second part, the third part, which is again S I Z. So, that will again give me sum over I, basically all S. So, every spin will give me S operating on 0. So, this will be n times S. So, I can straight away write this as n times S. N is the number of sides. Okay. So, this is H times n times S. Now, I have the other term minus half this term S I minus S j plus I j operating on 0. This term will immediately make all these, at every site this will make it 0. So, this contribution is just 0. So, that means life is so simple now because of this particular construction, the way I have rewritten the Hamiltonian, life becomes so simple. So, now I can see that it is an eigenstate. So, if I write H 0 equal to E 0 0, then my E 0 is minus half S square sum over I j j I j minus n H s. So, that is the so the first 1 and 2 that it is a ground state. So, I have established two things. Then I have not yet established it is a ground state. I have established that it is an eigenstate. So, 1 and 2 are done, that 0 is an eigenstate. To E 0 is equal to whatever we found out, right, minus half S square j I j minus n H s. The third one is still to be shown, that this is the lowest eigenvalue that you can ever find for this model with ferromagnetic J's. So, that is the thing that we have to do now. So, to do that, one uses a small trick, that is, one tries to write down another state. Suppose I can write down another state and I claim that its energy is lower than this energy E naught. If I can show that, then of course, I will immediately disprove this assertion that this ground state that I have chosen is not the right ground state. There are states which are with energies below this ground state. But suppose I cannot prove that, and I can show that this is the lower bound of any state, any energy that you can, for any eigenvalue that you find for any other state, and this is the lowest bound that you can have, then of course, I am home. I can claim that, okay, so that means this is the lowest energy eigenvalue, and therefore, this is the ground state. Okay. So, basically I will have to show that there is no other state whose energy is lower than this. So, let us just claim. So, I claim there is a state called 0 prime whose energy is lower than lower than E 0. So, E 0 prime, which is equal to 0 prime H 0 prime, is that my claim would be that this is the lower, this would be, I want to show whether this is lower than E 0. Okay. So, let us just write the Hamiltonian again. If all the j I j's are positive, which is what we are doing, then of course, this is the lower bound of the energy j I j maximum value of S I dot S j, right, minus H times maximum value of S I S Z I. So, this is obviously this is the lowest energy you can think of, right, you can have, because maximum value of this with a minus sign, maximum value of this with a minus sign. Okay. So, suppose I want to find out, and I claim that E 0 prime is a state for which is this, whose energy is this, E 0 prime is this energy. Okay. So, I will find this is the maximum, this is the minimum energy that you can think of, and then I will try to see if that minimum energy is bigger or less or equal to E 0. Okay. So, that is what I will find out. So, upper bound, this is the upper bound, this is the lower bound of the energy, right. Okay. So, what is this maximum of Si dot Sj? So, that requires some calculation. Let us just try to outline how you do it. Remember, Si plus Sj, this can form, both of them are S. So, the maximum they can have is 2S. Okay. So, then Si plus Sj square is 2S into 2S plus 1. So, this the square of this is 2S plus 2, and this is equal to Si square plus Sj square plus 2 Si dot Sj. So, I have the maximum on this side. Now, these two are basically S into S plus 1. So, S into S plus 1 plus S into S plus 1 plus 2 Si dot Sj. So, this I bring onto the other side. So, 4S square plus 2S minus 2S square, S plus S is minus 2S equal to 2 Si dot Sj. So, that means these give me 2S square and these two cancel. So, Si dot Sj equal to S square. So, that is the maximum that you can have Si dot Sj. Okay. Fine. So, maximum of Si dot Sj is S square. The only thing you should remember that I is not equal to j here. If I were equal to j, if I equal to j, then we already calculated this, we know because we are using it. So, in that case it will be just just the you can easily calculate it, right. I mean, it is I, if I equal to j, then this side is just 2s, 2si. So, Si square is S into S plus 1. Okay. So, so this, okay. So, this, let me just write down again. So, if I equal to j, then what do you have? Then Si dot Sj, Si dot Sj is S square, right, because it is just Si square, and that is equal to S into S plus 1. So, that is if I equal to j, but that is not the situation we have. Okay. So, what we have is I not equal to j, and this is not the situation we have, and so this is the maximum value of this operator j, max of Si dot Sj. Okay. And the maximum value of Sz I is how much? That is of course S. So, that means this thing that the minus half Jij maximum of Si dot Sj I not equal to j, remember, minus h somewhere I maximum of Zi is equal to minus half S square Jij somewhere Ij minus H n S. Now, look at it, this is equal to E0 that we obtained for the our original ground state, classical ground state, that we made an assumption that that is the same state that will apply here, our chosen ground state, which was this ground state, for this is the same energy. So, the lower bound of the energy of this Hamiltonian coincides with this value. So, the lower bound being equal to E0, there is no other state, there is no other energy or state for which the energy is below this one. So, that means this is the ground state. Okay. So, that is how this calculation goes, and so number 3 is also now proved. So, number 3, which is the ground, this 0 is the ground state. So, that has now been proved. So, we set out to do calculations on Heisenberg ferromagnet, and what we found out is that indeed the chosen ground state where all spins are up with full value of spin s is indeed the ground state. So, this is a very lucky situation where your classical intuitions work out and give you the ground state, the right ground state, that is the ground state, where the classical ground state and the quantum ground state, by classical ground state I mean the classically a state which is the lowest energy is all the states, all the spins are up. In quantum mechanics, of course, I have to write a corresponding wave function, and that is this direct product wave function of all the spins being attaining its maximum z component value, and that ground state, which is the classical analog, indeed is the ground state. So, for this case we are extremely lucky that we found the right ground state. But suppose these j I j's are negative, then of course, you have an anti-ferromagnetic situation, right. Spins, alternate spins will be like up and down, right. In one dimension, for example, this is how it should look like. Classically, that is what our intuition tells us. You can of course write this state as a product state again, but what you will find, just do the same thing that I did, just operate with H as I wrote down, and then you will see that this S j plus operator operating on these spins will not be 0. It will just raise the spins back to it just reduce the value of S from minus S to minus S plus 1. So, in spin half case, this will just reduce from, will go from minus half to plus half, that means it will just turn back up. So, it is not 0, and then if it turns up, then of course, you have a different state. So, you are operating on this ground state, you will not get back. So, suppose this is the ground state, new ground state for AFM, that the ground state for AFM that you chose, then the Hamiltonian operating on GAFM is not some energy E times GAFM. So, it is not even an eigenstate. So, that is a big problem, and that is says that this state is not even an eigenstate. So, let us not even bother about whether it is the ground state or not, and that complicates life a lot. So, I will not get into that. As I said, only in one dimension there exists a solution for that state.